Today we are going to talk about passive network synthesis. So coming to the passive network synthesis, in an electrical networks, it is broadly classified into analysis and synthesis. Coming to the analysis, we have a circuit and excitation is given. We need to derive a response for that circuit. That is excitation and a transfer function. We need to derive the response. So given electrical network, sources are given. We need to find out the current or a voltage across the network element. And the second topic is synthesis. Today we are going to talk about network synthesis. That is, the excitation and response characteristics are given. We need to realize a network. So realization of a network based on excitation and response characteristics. And we have seen in network analysis, we need to derive a response from a given network and its excitation. The solution was unique. So you would have gone to the many theorems and many laws in which you can derive for a particular response, whether it's a current across the network element or the voltage across the network element. But coming to the synthesis, there can be many solutions. It is not like an analysis part in which you would have a unique solution for a given problem. Here, for a given characteristic equation, that is excitation and response characteristic equation, we would like to find out the network for the characteristic equation. The network can be in many forms. So those forms here we will see is Foster form 1, Foster form 1, as well as there is a form 2 and Carr form 1 and 2. So prior we go in detail about realizing a network for a given excitation and response characteristic equation, we would like to know few terms, that is Hurwitz polynomial and positive real functions. So today's class we will discuss about Hurwitz polynomial, what it is and how we can tell whether it is the polynomial is Hurwitz or not, and whether the function is positive real function or not. So Hurwitz polynomial and PR function, that is positive real function. Coming to the Hurwitz polynomial, we can tell a polynomial P of S, that is in S domain, equation is written in the form something like a to the an s to the power n plus an minus 1 s to the power n minus 1, so on till a naught. A given polynomial, we would like to know whether it's Hurwitz polynomial or not. For that, a polynomial has to satisfy set of properties. That means polynomial to be an Hurwitz, all the roots of polynomial has to be in the left side of that of your S-plane. So let's go further for discussing about the Hurwitz polynomial. In that, the first condition is that the roots should lie on roots or the poles or the zeros, and as well as zeros should lie on the left side of the S-plane. And always the necessary condition for the polynomial to be a Hurwitz or not is when we have a continued fraction expansion. When we have a continued fraction expansion of that polynomial, the quotients which we derive, that has to be real and positive. That has to be positive quotients. So let's go in detail about Hurwitz polynomial. Once we finish this Hurwitz polynomial, we will go in detail about positive real functions. So we will need especially this term, that is positive real functions. The function has to be positive real. That means a characteristic equation, if it is given in the form of f of s, or you might know a given network has got z of s, impedance function, or y of s, correct? It has got numerator function and it has got a denominator function, almost like a polynomials. Numerator polynomial, denominator polynomial. Even your z of s has and f of s has. So these, whatever we have in a problem, that is a characteristic equation in the form of impedance or the admittance, these both has to be positive real functions in order to get, or in order to realize our network, or in order to synthesize our network. The must condition that the function should be positive real. But before we go in detail about the positive real functions, let's study about Hurwitz polynomial. So we will discuss about Hurwitz polynomial. Once we finish those, then we move further for Foster form 1 and 2. Especially Foster form 1 will give like impedance function, Foster form 2 will give for the admission functions, Core form 1 and 2, which will be a ladder circuit. We will discuss those in the next class. Coming to the Hurwitz polynomial, the function the polynomial p of s is said to be a Hurwitz if the poles of that should lie on the left side of S plane. That means a given a plane, correct, of its equation, characteristic equation, which has a 1 by s in the denominator, that represent a pole in the coordinate of that. That is, this is the j omega axis, this is sigma. So this represent in time domain a unit function, right? And the unit function u of t in Laplace is 1 by s. So that represent a pole in the origin. So here the system is stable. If we have two poles on the coordinates, so we definitely have 1 by s square. So whether this function is stable or not, because when we have a Laplace inverse, it will rise to a time function t. That means it is for input at t is equal to infinity, the output is also infinity, but it doesn't satisfy the stability, correct? So Hurwitz polynomial are the polynomials where the system should be stable, right? As we seen in the Routh-Hurwitz criteria in control systems, if all the first column of Routh-Hurwitz criteria is positive, then we say that system is stable. If any sign change occurs from positive to negative, then negative to positive, we say that there are two roots which lie on the right side of the S plane, correct? So stability is not reached. So the system is not stable. Stability is measured when we have a bounded input, we should have a bounded output. Then the system is said to be stable. But when we have two roots, then system is not stable. So when we cannot have multiple roots on the j omega axis. Clear? So for a polynomial said to be Hurwitz, we should not have multiple roots on the j omega axis. We can have a roots like this, one at j omega, another at minus j omega. This represent nothing but 1 by s square plus omega square, a sine function, which is nothing but BIBO stable. For any time t is equal to infinity, you see the response is between 1, that is plus 1 and minus 1, the amplitude of the sine, correct? So for any two poles lying on the j omega axis, this is simple poles lying on the j omega axis, we can say that system is BIBO stable. But if we have multiple roots on that, then the system is not stable. So the necessary and sufficient conditions for a system should be polynomial should to be said as a Hurwitz polynomial, that the roots should lie on the left side of the S plane, or there should be a simple roots lying on the j omega axis. If it lies at multiple roots, then system is not stable. It's not a Hurwitz. Coming to this p of s, the first, all the coefficients of p of s has to be positive and real. P of s, an s to the power n plus an minus 1 s to the power n minus 1, so on till a naught. All these coefficients, that is an minus 1, an minus 2, so on, a1 and a naught, all should be positive, correct? All should be positive and greater than 0. It should not be 0 also. If it's 0, then some of the s terms will be missing. If any term missing, then it is not a Hurwitz polynomial. Or in the other sense, if it is negative, any of the coefficients are negative, then it's not a Hurwitz polynomial. And the one more important necessary conditions, as we said, continued fraction expansion. Continued fraction expansion. This we are discussing in order to make us comfortable when we are into core form of realization of network. It means given an equation, we have to determine core form 1 or core form 2, which is similar to the ladder structure. We need this continued fraction expansion. That's why I am discussing this Hurwitz polynomial. A continued fraction expansion, the quotients which results from this has to be positive. If any negative term comes into picture, then it is not a Hurwitz polynomial. So taking an example, we will go further in deriving whether a polynomial is Hurwitz or not. As we said, quotients and continued fraction expansion, this P of S has to be in the form of numerator by denominator. That means P of S should be somehow made in form of numerator function divided by denominator function. How we can have a numerator function divided by denominator function is, we just find out all the even polynomials and all the polynomials in two parts. M of S representing the even polynomials and N of S representing the odd polynomials. How? As I said, all the S terms which has got order in positive will be called as a even. Let's consider here an s to the power n plus an minus 2 s to the power n minus 2, so on till a naught. These are we will call even polynomials. Even polynomial. And from P of S, if I represent N of S in terms of an minus 1 s to the power n minus 1, so here M of S is even and N of S is odd only if N is even and M of S equation is odd if N is odd. Correct? If I have N is equal to something 4, so A4 s to the power 4 plus A2 s to the power 2 plus so on up to A naught will be a even polynomial, and A3 s to the power 3 plus A1 s will be an odd polynomial. If my n is odd, then it will be vice versa, right? So to have continued fraction expansion, we will do M of S by N of S. We will have a continued fraction expansion of this, and the quotient has to be positive in order to tell that it is Hurwitz polynomial. So let's go on solving the problem, taking one example. So before we go further into solving the problems, let's go in the again basic details about M of S by N of S. So as I said, M of S by N of S is a odd and even functions or odd and even polynomial. That means we have got an s to the power n plus an minus 2 s to the power n minus 2, so on till a naught, and the denominator polynomial is nothing but an minus 1 s to the power n minus 1 plus an minus 3 s to the power n minus 3, so on till a1s. So here we see that our numerator has a 1 degree greater than that of your denominator. Correct? So the necessary condition is that n minus m or numerator order minus the denominator order should be less than or equal to 1. That is, whenever we have a numerator polynomial divided by denominator polynomial, the order difference should not be more than 1. What happens if more than 1 is there in the numerator? In the equation, numerator equations gives rise to a zeros, denominator equation gives rise to the poles, correct? So if numerator is having 1 degree greater than that of your denominator, that means one pole should come from infinity and settle onto the 0. If our numerator has got 2 degree greater than that of your denominator, then that has to be 2 poles coming from the infinity and settle onto the zeros. So that will impair the stability. So we will go with the fact that numerator minus denominator should be less than or equal to 1 in order to find out whether it is Hurwitz polynomial or not. So continued fraction expansion. What we do? We divide this numerator by our denominator. So we end up with the first an by an minus 1, s to the power n by s to the power n minus 1 is s, plus here we have an minus 2 dash so on till a naught dash. Once we do a first division, this is nothing but the first quotient which resulted from the division of the denominator from numerator. When you see the second function, first, second, you see the numerator degree is 1 less than that of your denominator. We want to go for again division of numerator from denominator. So what we do, we inverse. So we will write this is now n of s, right? N of s. But now numerator is nothing but m1 of s, some other polynomial. So we will write n of s divided by m1 of s. So before we did fraction expansion for m of s by n of s, we got the first quotient into s, plus as the denominator is having 1 degree greater than that of your denominator, we have to inverse that, then we go for further division. So this n of s will be having 1 degree greater than that of your denominator m of s, m1 of s. So this in the end will be continued till we get the last element. So this will be like 1 by alpha 2s plus 1 by alpha 3s, so on till the nth element will be alpha n. Yes, correct. These are the quotients. We will see how we can telling it as quotients in a problem. But the quotients which are derived from the continued fraction expansion, so which are nothing but alpha I is standing from 1 to n, has to be greater than or equal to 0, greater than 0, which has to be positive, greater than or equal to 0. So if we get a negative term, that means a polynomial is not a Hurwitz polynomial, right? So let's do a problem in which we will discuss whether the polynomial is Hurwitz or not. No problem. So as we are discussing continued fraction expansion, consider this polynomial p of s, nothing but s to the power 4 plus 3s to the power 3 plus 2s square plus s plus 1. Whereas consider this p of s, almost similar, consider let's take 3s cube, 2s square, so if you see the polynomial p1 p of s, that is the first question to determine whether it's a polynomial, Hurwitz polynomial or not. S to the power 4, s to the power 3, s to the power 2, s to the power 1, s to the power 0. So we can go further for solving this. And if this question is missing with the term yes, and if I write like this, so definitely it is by inspection itself we can tell that the function is not a polynomial, is not a Hurwitz polynomial, because it's missing the term s to the power 1, that is a1 is 0, correct, or s term is missing. So by default with the inspection we can tell that this is not a Hurwitz polynomial. Coming to this second, s to the power 4, 3 square, 2 square s cube plus 2 square minus s plus 1, s plus 2. The term here, the second term, a1 is negative. So as I said, it should be positive, correct, and real. Then only we can tell, when we can go further for finding out whether it's Hurwitz polynomial or not. So hence it is not a Hurwitz polynomial. So we will see when all the terms are present and whether the polynomial is Hurwitz or not. Let's take the third problem. P of s to the power 4 so we have all the coefficients which are positive. Here there is no s term missing. S to the power 4, s to the power 3, s to the power 2, s to the power 1 and s to the power 0. All the terms are there. Then we don't know whether this is Hurwitz polynomial or not. So we have to, as we said, we have to go for the continued fraction expansion. For that we have to find out the odd polynomials and even polynomials, m of s plus n of s. So m of s from this polynomial is, the even polynomial is s to the power 4, 5 square plus 4. Whereas the odd polynomial n of s is s to the power 3 plus 3s. So we have to do m of s by n of s. We have s to the power 4 plus 5 square plus 4, which is of order 4, and n of s is order of 3, so which is 1 degree greater than that of your denominator. 1 degree greater than that of your denominator, the numerator has. So we have to write continued fraction expansion. That means this has to be dividing this. The denominator has to divide numerator. S to the power 3 plus 3s, s to the power 4, 5 square plus 4. When we can have order s to the power 4, when we multiply s, correct? S to the power 4, 3 square. So which results into 2 square plus 4. So we can write this in the form of quotient is what? S plus the result remainder 2 square plus 4 divided by divisor is s cube plus 3s. As we said, alpha 1 here is 1, definitely is positive. We can go further for the continued fraction expansion of this. You can see the numerator is of order 1 degree less than that of your denominator. So what we have to do? Invert this. So we can write s plus 1 by. Now our n of s is there. m1 of s, m of s becomes m1 of s, that is 2 square plus 4. That we have to go further for dividing. That is s cube plus 3s, divide that with 2 square plus 4. Now we have to divide s cube plus 3s divided by 2 square. So 2 square plus 4 should divide this. So I can write here only, no? S cube plus 3s. When we can have s cube, when we multiply s by 2. Correct? So s2 square will reduce to s cube into 2s by 2 plus 4 into s by 2 is 2s. What is the result? Yes. Right? So I can write this term as s plus 1 by, this is s by 2 plus, again go further. So I have to divide this s from this. Okay? 2 square plus 4. So we have to have 2s, 2 square, we will get 4, and we have to divide s, 4s, s by 4. So when we have further, we will get s by 2, 2s plus 1 by s by 4. Correct? So this way we have to do a continued fraction expansion. In the end, alpha 1, alpha 2, alpha 3, alpha 4. All alpha. Alpha 1 is 1, alpha 2 is 1 by 2, alpha 3 is 2, alpha 4 is 1 by 4. All those coefficients, all those quotients are greater than 0. Right? Hence, we can tell that the given polynomial in the question, that is third equation, that is P of S, is yes, it is Hurwitz polynomial. Let's see one more problem where which we have to derive whether it is a Hurwitz polynomial or not. Let's take the fourth problem. The P of S is s to the power 4 to s cube plus 4s square plus 3s plus 2. So the necessary condition is that find out the continued fraction expansion and let us know whether it is Hurwitz polynomial or not. So for this to determine whether it is Hurwitz polynomial or not, we have to find out m of s. So what is m of s? M of s is the even polynomial, s to the power 4, 4s square plus 2. Whereas n of s is s cube plus 3s. Please try yourself and find out whether all the quotients are leading to positive quotients or not. Okay? Once you find out, then continue this video and find out the answer is same or not. So, m of s by n of s. So what we have to do, we have to differentiate denominator from numerator in a continued fraction expansion way, and then we have to tell whether it is a coefficients is positive or not. So s cube plus 3s. Once you multiply s, you get 4s to the power 4 and 3s square. So you will get with s square plus 2. Now, when I did the expansion, first element needed me alpha 1s, that is 1s. So now I have to divide this from this. S cube 3s. Yes, I have to multiply s cube plus 2s. This is s. So when we go further and find out that s cube plus 3s, s to the power 4, 4s square plus 2, my continued fraction expansion gave me all the quotients are positive. Okay? Hence it is Hurwitz polynomial. Let's take the same problem and just alter the one term. Let's take this 2, a fifth problem, and let us know whether it's Hurwitz polynomial or not. So we just change 4 as 2. Solve by yourself and let us know at the end it's Hurwitz polynomial or not. Once you find out, then continue this video and just check out the same results came into picture or not. M of s is s square plus s to the power 4, 2s square plus 2. N of s is s cube plus 3s. So we have s square. When we go further, s cube plus 3s. To get s cube, minus s cube minus 2s. We'll end up with 5s minus s by 5 So we have the controlled fraction expansion as the first term is s, second term we have minus s, the third term minus s by 5, the fourth term 5s by 2. You can see the quotients which are in the second and third term are negative. Hence we will tell that this polynomial is not a Hurwitz polynomial. So given any polynomial p of s, find out its even polynomial and odd polynomial, then find out the controlled fraction expansion. If any quotient leads to a negative term, then tell it's not a Hurwitz polynomial. If all the quotients which are alpha is positive greater than 0, then you can tell that it's a Hurwitz polynomial. So I have taken the problem which is nothing but s to the power 4 terms. Even the problem will be having s to the power 5. S to the power 4, s to the power 5 in this kind. That time my n of s will be having a 1 degree greater than that of your denominator, because s to the power 5 is the odd polynomial which is having 1 degree greater than that of your even polynomial. So we have to go for the controlled fraction expansion of n of s by m of s. Okay, this is all about Hurwitz polynomial. Then we move on to the positive real functions. Coming to the positive real functions, so it's similar to the Hurwitz polynomial. There are some set of properties which it should satisfy. The function should satisfy in order to tell that it is positive real functions. So a function f of s is said to be positive real function if the roots of the function lies on the left side of the s-plane and it should have a simplex poles lying on the j omega axis. If it has got simplex poles lying on the j omega axis, then the residue of that poles should be real and positive. We will see those in the problem, but that is one of the necessary conditions. So the main important condition is that f of s should be positive real functions, that it should satisfy the real part of f of s should be greater than or equal to 0 for a real part of s greater than or equal to 0. That means a function f of s has to be greater, the real part of f of s has to be greater than or equal to 0 for a real part of s greater than or equal to 0. That is the necessary condition in order to tell whether the function is positive real. The first condition, all the poles and zeros should lie on the left side of this plane. The second condition, if there is any simplex roots lying on the j omega axis, the residue of that root has to be real or greater than or equal to 0. Real and positive. It should not be negative. And the third one is that this real part of s should be greater than or equal to 0 for real part of s greater than or equal to 0. So, if consider a given function is positive real functions. If function f of s is positive real functions, then 1 by f of s is also a positive real function. Or if f of s is written in terms of two functions, f of s is written in terms of two functions, that is f1 of s and f2 of s. If f1 of s is and f2 of s both are positive real functions, then hence the addition of those two functions is also a positive real function. But When it comes to the negative term, it may not be true. That is, f1 of s minus f2 of s may or may not be positive real functions. We have to find out. But if f1 of s and f2 of s are positive real functions, definitely f of s is also positive real functions. And f of s, let's consider it's in the form of multiplication. That is, consider w of s and f1 of s, some other functions. W of s is function, f1 of s is function. If w of s is positive real function, as well as f1 of s is also a positive real function, then hence the multiplication will also be a positive real function. So if addition, multiplication or inversion is also a positive real function for given functions are positive. But subtraction may or may not be a positive real functions. Having those, let's see when we can have a function to be a positive real function. Let's give a polynomial an s to the power n minus 1, so an so given a function, numerator is there, denominator is there, and we know that all the poles, all the roots which are derived from the denominator function should be lying in the left hand of this plane, and the degree of the denominator compared to the numerator should not be greater than 1. It will affect it will impair the stability, so n minus m should be less than or equal to 1. So we will go with the consider n minus m is equal to 1. If I put s is equal to j omega and solve further, real part of f of j omega should give you greater than 0 for omega greater than omega greater than equal to 0. Why this this is the necessary condition wherein which we tell whether it's positive real functions or not. Real part of f of j omega greater than equal to 0. The application behind this is we are talking about passive network synthesis. So once we do a synthesis, the character equation of this form, excitation to response character equation, will lead you some kind of RLC circuit where there is no source. The network which we synthesize is passive. So if it consists of an RLC, RL maybe C, or some other configurations in which a single port is there, f of s representing RLC. So this RLC are the elements which absorbs the power. So the average power P which is absorbed is 1 by 2. RLC represents Z of j omega into I square the current flowing. So P average, so the real part of this. Real part of this should be greater than or equal to 0. That's the must condition because the power consumed is positive. Right? Power consumed is definitely there. Consumption is there because of RLC, passive network. So from this I is greater than 1, I square definitely greater than 0, 1 by 2 is greater than 0. So real part of Z of j omega is greater than or equal to 0. This is the must condition in order to synthesize the network. Real part Z of j omega. This Z of j omega nothing but f of s. F of s can be written in the form of Z of s as well as y of s. Given network can be found out for Z of s as well as for y of s. Right? So we will see some of the equations. We will take some examples and we will know whether they are positive real functions or not. So as I said, 3 conditions are required. Okay. So let's see those conditions. Let me take one simple example in which my f of s is s plus 3 divided by s plus 1. S plus 3 divided by s plus 1. So the first step is that we will know whether the poles and zeros are lying on the left side of s plane. Yes, the zeros. Which are the zeros? S is equal to minus 3. Yes, they represent here. When I represent poles and zeros, s is equal to minus 3. At this point we have got a 0, and pole is lying at s is equal to minus 1. So at s is equal to minus 1 the pole lies. Pole represent as x, 0 represent as 0. Okay, so we see from the figure of the graph that s, my poles and zeros are left side of the s plane. First condition satisfied. Let's see the second condition. It says that if there is a simplex root lying on the j omega axis, we need to find out the residue. Residue are real or positive. As there is no pole lying on the j omega axis, this step is not necessary. The third step, that f of s, that is real part of f of j omega, should be greater than equal to 0 for j omega greater than equal to 0. Correct? Then we can have f of j omega. When I put f of j omega is j omega plus 3 by j omega plus 1. Then we can have real part and imaginary part. When I multiply j omega 1 minus j omega 1 plus j omega. So when I multiply that, 1 minus j omega. So in the denominator we will have omega square plus 1, a square minus b square. In the numerator, omega square plus 3. This is the real part. Minus j omega minus 3 j omega. So it is minus 2 j omega. So the real part of this is omega square plus 3 divided by omega square plus 1, and the imaginary part is 2 omega by omega square plus 1. Correct? So the real part of this f of j omega is this. Has to be greater than equal to 0 for omega to 0. So keep omega 0, 3 by 1, omega 1, yes, omega square in the denominator. So at all the values, omega is equal to 0 to infinity, you will get positive value for the f of real part of j omega. Hence all my conditions satisfied, we can tell that yes, my function is positive function, positive real function, a PR function, positive real function. Let's take the second problem. But prior going to that, I would like to tell, if there are polynomial in the numerator and denominator of order greater than 3 or 4, in the denominator of order greater than 2, it will be difficult to find out the real part and imaginary part. Correct? So how to solve that? So taking the same example, so let's see how to solve the shortcut. Alright, in necessary conditions, we will avoid the necessary conditions when my real part of f of j omega can be greater than equal to 0. When? See, if f of s is given, f of s can be, if higher order degree is there, we can write numerator polynomial as m1 of s plus n1 of s, right? Because numerator is also having odd and even polynomials, denominator is also having odd and even polynomials. So m1 of s is even polynomial of the numerator, n1 of s is odd polynomial of numerator. Similarly, m2 of s is even polynomial of denominator, m2 of s is odd polynomial of denominator. So to get a real part of this, real part of f of s. I need to multiply the denominator in the conjugate form, m2 of s minus into of s, m2 of s minus n2 of s. When I multiply, what happens? My denominator will be m2 of s square minus n2 of s square, right? Or I can tell m square or n square. m2 square minus n2 square. And the numerator, what happens? m1 into m2 minus n1 into n2, as well as m1 n2, m1 into minus n2, n1 minus m2. So I will write the first term, m1 of s, m2 of s minus n1 of s, n2 of s. And I will write the other term as like this. Denominator is m2 square s minus n2 square s, and the numerator is first I will take this m2 into n1, m2 of s into n1 of s minus this m1 of s into n2 of s. Why I wrote this way is that when you do a solution for this multiplication, this will be a imaginary part and this will be a real part, and we are interested in real part of f of j omega. As we see in the previous case, s plus 3 divided by s plus 2, we ended up with omega square plus 2 divided by somewhere in that form, right? So that term will be the first one, and we seen the denominator is always positive because it was in this form of omega square plus 1, omega square plus 1 in the denominator, right? So we are not bothered about this, whether it is greater than 0 or not. We are bothered real part of f of j omega. Real part of this is greater than j omega, and we know that denominator, when we multiply with the conjugate, will lead to a positive value, omega square plus 1 or whatever the form. Denominator will be positive. Only the necessary condition will be now is that m1, m2 minus n1, n2 is greater than equal to 0 or not. That is m1 of s into m2 of s minus n1 of s into n2 of s is greater than equal to 0 for omega greater than equal to 0. So in order to find out for this, we have to find out m1, n1, m2, n2, and just multiply m1, m2 minus n1, n2, find out whether they are greater than 0. For this given problem, we know that it is a PR function, but let's go in whether this condition satisfies m1, m2 minus n1, n2 greater than equal to 0 or not. So here I want to know m1 of s, n1 of s, m2 of s, n2 of s. Which is m1 in this? m1 is a even polynomial. So is my 3 is even polynomial? Odd polynomial s to the power 3 is s to the power 0 is even polynomial. n1 of s is having s. So this is, so my m1 of s is 3, n1 of s is yes, and my m2 of s is what? Yes. Any guesses? Yes, my 1 is m2 of s, whereas n2 of s will be simply straight away s. So when I have m1 minus m2 minus n1 minus n1 into n2, m1 m2 minus n1 n2, sorry for that, m1 m2 minus n1 n2. So m1 is 3, m2 is 1, 3, m1 m2 minus n1 n2 minus n1 and n2. Yes, s into s, that is minus s square, right? We have to find out whether it is greater than or equal to 0 or not. This is the necessary condition. Put s is equal to j omega. What happens? Put s is equal to j omega. When I put s is equal to j omega, minus times of j square into omega square, minus into minus j square is positive 1. So this will leads to 3 plus omega square greater than or equal to 0. So this, is this true? In my 3 plus omega square, is it greater than equal to 0 for all of this? Yes, keep omega is equal to 0, we will have f of s, f of j omega is 3, real part of that. Keep on increasing the omega value, definitely my term will be increasing, it will be positive. Hence, this will be a positive real functions. For the simple problem, it looks tedious. Why to go, simply we can multiply 1 minus j omega in the numerator and denominator, we can go further for solving this. But if we have a higher order polynomial, we will take in the next problem, higher order polynomial, then whether to find out whether it is a positive real function or not, we need to satisfy m1 n2 minus n1 n2 greater than or equal to 0 or not. Let's take the second problem. Yes, let's take the second problem, that is f of s square 6s plus 5 square 9s plus 40. Test whether is it a PR function or not. So test whether is it a positive real functions or not. So as we said, to test there are 3 tests we have to do. First is all the poles and zeros should lie on the left side of the S-plane. The second, if any residue simplex roots are lying on the geometry axis, so we have to find out the residue of that, whether it is positive or real or not. And third one is real part of j omega is greater than or equal to 0. So the first, so f of s, to find out the poles and zeros. The zeros of this numerator function is s plus 5 into s plus 1, correct? This is nothing but s square plus 6s plus 5. The denominator we can write s plus 7, s plus 2. S plus 7 and s plus 2. S square plus 9s plus 14. So, from this we can understand that the zeros are minus 5 comma minus 1 and the poles are minus 7 comma minus 2. So, if I plot the j omega axis, sigma j omega, S domain, at minus 1 I have a 0, represent a 0, and at 2 I have a pole minus 2, at 5 I have a 0, minus 5, at 7 I have again a pole, minus 7. So if you see, all those are lying on the sigma axis but left side of the S-plane, then hence this is stable system. So we can go further for the next step, testing, that is residue test. As we see, there are no simplex roots lying on the geometry axis, no need to test the second. So the residue test is omitted. The third test is we have to find out real part of f of j omega, whether it is greater than or equal to 0 for omega greater than or equal to 0. To test this, we have seen in the previous problem that in order to find out, simply don't multiply s 7 minus s or minus j omega plus 2 minus j omega plus 7, multiply that. Straight away we will find out m1, m2 minus n1, n2, whether it is greater than or equal to 0 or not. To get m1, m2 greater than or equal to, m1, m2 minus n1, n2 greater than or equal to 0, first find out which is m1 and m2. When I see m1 is the even polynomial of the numerator. Even polynomial of the numerator is s square plus 5. That is s square plus 5. The odd polynomial is 6s. Odd polynomial n1 is 6s. And I see the denominator. m2 is what? It is s square plus 14. S square plus 14. And the n2 is, the odd polynomial is 9s. So we just have to multiply in this way. S square plus 5 multiplied with s square plus 14 minus N1 into 6 into 9, 54 square should be greater than or equal to 0. So just find out after multiplication what is the result. So s to the power 4 5u square plus 14 square is 19 square. So 5u into 14 is 70 minus 54 square greater than or equal to 0. So if you see s to the power 4, we have 19 minus 54. What is the result? 35. 35 square plus 70 should give you greater than or equal to 0. So put s is equal to j omega. When I put s is equal to j omega, s to the power 4 leads to what? J to the power 4 is positive 1. J to the power 4 is positive 1. Omega to the power 4. We have omega to the power 4. Minus 35. S to the power 2. J omega to the power 2. We will get minus omega square. So plus 35 becomes omega square. Plus 70. Greater than or equal to 0 or not? Please put the value of omega greater than or equal to 0. Hence my real part of f of j omega is greater than or equal to, definitely will be greater than 0. So hence our function PR is positive real functions. Okay.